From the physics department at Williams College. Welcome back to the second lecture in the physics of musical sound. Last time we talked about how the physical properties of simple musical instruments like a string determine both the musical pitch those instruments play as well as the characteristic tone quality or timbre of the instrument. The pitch, you'll remember, was determined by the frequency of the sound wave. That is, by the number of crests of compressed air that arrive at your ear every second. So that frequency was measured in hertz, and a higher frequency corresponded to a higher musical pitch. The timbre of the instrument was determined not by the frequency of the wave, but by the shape of that wave, by the number of complicated wiggles and bumps inside each cycle of the wave, which is in turn determined by the mixture of shaking in each of the resonant motions of the instrument. In this lecture, we're going to answer several more important questions. In particular, we want to think about how the construction of the instrument, as well as the construction of our own auditory system, affects the sound that we hear. To think about that, we first need to think about how the sound created at the core of the instrument, for example, created on the string of a violin, is transmitted out to the world. First, how that string is excited by plucking or bowing it, and then how that shaking string transmits its energy to the body of the instrument, how the body of the instrument shakes the air, and finally how that shaking air goes into our ears and ultimately causes our brain to understand a particular sound. So to start with, we want to think about the question of how we excite a vibration and how the different sorts of excitation we might do would change the timbre or the spectrum of the sound that's created. So we want to start first by simply thinking about plucking a string, as one would on a guitar or perhaps on a violin if you were playing pizzicato. Here, we can imagine the shape of a string that might take place if we grabbed the string right in the middle, pulled it, and just let go. And we want to ask how we would decide which mixture of resonant motions that string can have. Remember, this is our menu of choices. Which motions that we would excite of these resonances by plucking right in the middle there. It turns out that figuring out how much of each of these motions you get for a given excitation of the string is just a simple recipe put together by a French mathematician named Fourier. The mathematicians claim this guy, but I think he was really a physicist. Here's what you do. You draw the shape of the string just as you're about to release it from the pluck. And then you look at your menu of possible string motions and think about how you might need to add them together to create that shape that you're plucking. So let's look at this example. Our pluck is right in the middle, so we want our string to be pulled away from its center point right most at the middle. So we're going to need a lot of the vibration in the fundamental, this lowest frequency motion. But that's kind of curved. It's not pointy like our pluck, so that's not the only motion that's going to take place. You can see that this kind of curves over too slowly and gently compared to this triangle. So we're going to need to add in some of the vibrations that represent more rapidly changing motions. Now you might say to yourself, maybe we should add in some of this motion in the second resonance. But I don't want to use that one. What's wrong with that one? This one has a node right in the middle of the string. It has no motion whatsoever at the center, and we're trying to create something that has the maximum displacement, the biggest motion in the center. So we don't want to use this second one at all. And for the very same reason, we're not going to want to use any of this fourth one. It has a node in the center. or any of the 6th one, or the 8th one, none of the ones that are multiples of 2. All of those guys have nodes at the center, and they're what we call anti-symmetric. They're opposite from left to right. This guy is the same from left to right. So we know we only are going to want motion in the odd harmonics, and that's exactly how we're going to put this guy together. We'll need a lot of the fundamental, a little bit of the 3rd harmonic, which we'll add in the middle and take away on the edges there, so that gives us a steeper drop off to our shape, a little bit more of the 5th and the 7th, and decreasing amounts of each of the odd harmonics going up from there. So here you see the harmonic numbers and the amplitude. As we said, none of the 2nd, 4th, or 6th. If we have an amplitude of 1 for this lowest harmonic, we'll only want a 9th as much for the 3rd, a 25th as much for the 5th, a 49th as much for the 7th, and you can probably see how this goes, right? This is this number squared that goes in the denominator. So it drops off pretty quickly. And you'll remember from last time that we sometimes, instead of writing down these numbers, just draw a spectrum, which tells us how much motion for each of the harmonics we should include. So here we have a lot for F1, that's the fundamental, a little bit for the 3rd, less for the 5th and 7th, and even less as we go up to the odd harmonics. Okay, so that's if we grab our string and pull exactly symmetrically right in the middle. And we know that the mixture of frequencies we include here tells us something about the timbre of the sound that we'll get. Perhaps if you play the guitar, you know that you get a different timbre of sound, a different sound quality, depending on where you pluck the string, whether you pluck it up close to the bridge or further down over one of the air holes. And we can think about why that would be by briefly redoing this exercise. Imagine that we pluck the string someplace else. So here we've plucked in a much more asymmetric way. We've chosen to pluck about a 5th of the way from the end of the string. And we want to think again, a la Mr. Follier, how we should put together these different resonant motions to create that shape. Again, we'll need some of the fundamental that just says, you know, go up somewhere towards the middle. But now, because this is an asymmetric shape, we can include these asymmetric 2nd, 4th, and 6th harmonics, which we had to exclude for the symmetric situation. So you can see here what we want is more motion to the left, less motion to the right, and that's exactly what the 2nd gives us, up on the left, my left, down on the right, okay? We'll still need some 3rd harmonic and some 4th harmonic. Here's a funny thing. It seems that we don't want any 5th harmonic at all. Why is that? Well, where do we want our maximum motion here? We want the biggest displacement exactly 1/5 of the way from the end of the string. If we go down here and look at our 5th harmonic, 1, 2, 3, 4, 5, our 5th harmonic is, by definition, the motion that has a node, exactly no motion, 1/5 of the way from the end of the string. So that guy doesn't get to partake in this motion. So there's no 5th harmonic. And if I were adding it all the way out further, I'd find no 10th harmonic, no 15th harmonic, no 20th harmonic. All of those guys have nodes right here. So overall, how does the spectrum change when I change the location of the pluck? I've added in my even harmonics here, and I've also actually got more amplitude in the high harmonics in general. So perhaps you remember that for the symmetric pluck, if this was 1, the amount I had at the 3rd harmonic was only 1/9 as much. Here at the 3rd harmonic, I have almost 20% as much, so a 5th. So I've got more high harmonics in general here, as well as missing this 5th harmonic that I didn't have before. So the result is that we've got more high harmonics vibrating when we pluck closer to the end. And perceptually, we'll talk about why this is closer to the end, perceptually having more of the high harmonics vibrating tends to sound to us like a rougher or a sharper sound, more like a clarinet, less like a flute, for example. Okay? So where you pluck and how you pluck matters. And you might say to yourself, well, this matters to guitar players, but most other folks don't really get to decide where they pluck the string. This actually turns out to be important as well in the construction of the piano. Perhaps you remember from the first lecture this scale I showed you that comes from thinking about what notes are produced by the harmonics of a string whose fundamental is this low C 2 octaves below middle C on the piano. You remember we said here's the fundamental, the second, the third, the fourth harmonic, all playing nice notes in a sequence until you get up to this 7th harmonic. And I mentioned that this 7th harmonic plays a note that kind of doesn't really belong on the scale. It's sort of trying to be a B flat, but it's almost a third of a semitone flat. So if I played this harmonic along with a regular B flat, just from hitting the B flat key on the piano, they would sound terrible together. It would sound like two beginning violinists trying and failing to play the same note, right? Because this one would be flat, really ugly and flat, compared to the true B flat on the piano. So this is a problem. If you actually have a piano string, which is supposed to be this note, and has this as all its harmonics, and you're playing a chord that involves also hitting that note on the piano, you'll get this nasty, mistuned, horrible sound that is quite objectionable to the ear. And you'll notice that there's a problem again actually up here at the 14th harmonic. So the designers of pianos said, wouldn't it be great if we could find a way to strike the string so that the 7th harmonic and the 14th harmonic don't vibrate? So that when you pluck it, or actually strike it with a hammer in the case of the piano, these vibrations don't happen. And of course you know exactly how to do that, right? If I'm plucking in the middle, I don't get any 2nd harmonic. If I'm plucking a 5th away from the end, I don't get any 5th harmonic. If I don't want any 7th harmonic, I should pluck or strike the string exactly 1/7 of the way from the end. If you open your piano and measure, you will see that the hammers are designed to strike the string 1/7 of the way from its end. It's in order to eliminate the 7th and the 14th harmonics from the spectrum that the strings produce when they're struck. So it matters not just to guitar players. Okay, so another question that comes up is the tuning of the piano. You can begin to see from my last example that when you're tuning a piano, you have a lot to think about. You have to think not just about how, for example, this note sounds with the octave above, not just how the fundamental of this note sounds with the fundamental of that note, but actually how all of the harmonics of this low note, right, which include this note, and this note, and this note, and a whole bunch of notes above them, how all of those vibrations will fit in with the vibrations from the higher notes. And one of the problems is that this beautiful picture I showed you in the last lecture, where each of these frequencies was a perfect multiple of that lowest one, and everything was dreamy and idealistic in the physics sense of dreamy and idealistic, everything was perfect. It's not quite true, which breaks my heart. Why is it not quite true? Remember this speed right here? The speed with which a wave makes its way along from one place to another? I said it didn't matter how we shook it. It always goes from one place to the other at the same speed because the stiffness of the rod is the same and the mass of the balls is the same. But strings aren't really like that. Strings are actually get stiffer if you try to shake them more quickly and with tighter bends. You probably know this. Try bending a piece of metal. If you bend it gently or bend it sharply, it's actually different. So this speed actually gets a little bit bigger as you go towards these higher harmonics. The string behaves differently. So the speed increases a little bit, and that means the frequency increases a little bit. So, from what it should be. So what happens is these harmonics get a little bit higher frequency than they would be in the ideal case because of the extra stiffness of the string at high frequencies, and that means they end up tuned a little bit sharp, a little bit too high frequency. So real piano tuners, actually when they're tuning the piano, they do what's called stretching the octave. So they tune each octave from here to here at just a little bit more than double the frequency. And that's because they want to tune this upper note so that it matches not quite just twice the frequency of the lower note, but also so it matches nicely the harmonics, and especially the high harmonics of the lower notes. So real tuning is not quite ideal like this, but it's pretty close. Okay, one other thing I wanted to mention, although we've been talking mostly about string instruments and how they're excited, this idea that the way you excite the system influences the balance of the harmonics you create applies to every kind of instrument. It definitely applies, for example, to this most simple 19th century wind instrument here, which normally just plays this note. But if I blow it hard enough, and I'm not a wind player, I can get a completely different note out. Indeed, those seem to be an octave apart, right? So it looks like I've got maybe a fundamental and a first harmonic here. Right? So all I'm doing is changing the way I excite the system, and I've changed the balance of the harmonics that I've created. So we've talked some about the way the spectrum is affected if we pluck the string in a particular location, relevant to guitars, to the striking of piano notes, and to violins pizzicato. But as you know, usually many stringed instruments are not plucked, but rather bowed. So we can think a little bit about the bowing mechanism and how it excites the string and how that affects the timbre of the instrument. So let me first show you a little bit about how bowing actually works. This is an animation that's going to show you the bow moving across the string. And the general idea here is that the bow sometimes sticks to the string and pulls it along with it. So we actually have the bow push into the string, and when the bow is moved, the string moves as well, just by friction. But eventually that pulling has to stop. The string can't move a foot out of place. It can only move a few millimeters. And eventually that friction breaks, and the bow keeps moving, and the string snaps back and goes the other way. And then after a while it'll stick again and pull and then snap back. Okay? So there's this stick-slip mechanism that happens. So it's almost like the bow is actually plucking the string repetitively. Pull and let go. Pull and let go. And the way to think about when it's going to grab again is to notice that because we're plucking, we're going to create a little disturbance, a little wave, that's then going to propagate along the string, come to the end of the instrument, and bounce back. And it's when that bouncing pulse returns to the bow that you get sticking again. So it's a sort of repetitive plucking that's set by the time it takes the pulse to go to the end and come back. Let's see if we can make that work. So there it's slipping, it's going to stick again. Here comes the pulse back around. It's going to slip, come back and stick when it hits the bow again. Okay? So although you think of bowing as this very continuous process, it's actually essentially a repetitive, periodic plucking of the string. So what should we notice about this bowing? So first of all, the amount that you actually displace the string, the strength of the pluck, how hard you're pulling the string, has to do with how far the string is able to get pulled while it's sticking to the bow before it finally lets go. And as you can imagine, when two things are pushed hard into one another, they tend to stick to each other more by friction. And so if the bow is pushing hard on the string, it's going to be able to pull the string farther before the string snaps back. Okay? And that's what string players will recognize, that the harder you push with the bow, the louder the sound you produce. That's because the harder you push with the bow, the further you pull the string before it slips away, and the further you pull the string, it's just like plucking it harder. Okay? So more bow pressure gives you more volume because it's giving you bigger individual plucks. It's also true that the place on the string that you bow will influence both the loudness of the sound and the timbre of the sound. So if you bow in the middle and you're able to, let's say, pull the string away this distance, you'll get a vibration that's about that big. If you're able to get the end of the string to move up and down by the same amount, then the middle has to be moving even more because of the shape that's required for the fundamental vibration. So if you bow up close to the end of the string, which means bowing up by the bridge for a violin, you'll also get a louder sound for the same amplitude of string motion. Okay, so it gives you more loudness to play by the bridge. What about the sound quality? So we should think about what kind of wave we're creating here with this sticking and slipping mechanism. And you can see it's sort of asymmetric. It looks asymmetric here, and it's also asymmetric in time because you're pulling gradually and then letting go suddenly. So the kind of wave of sound you're going to create is gradually pulling and then suddenly letting go, very asymmetric. And to think about the timbre of the sound, again, we need to try to create this sort of sawtooth wave by adding up these nice smooth waves that come from vibrations of the individual resonances of the string system. So I've put together some waves here that might look a little crazy. Here's the fundamental, going up and down 3 times, one for each of the crests of the sawtooth. And when I add the fundamental to these higher resonances, here's a good approximation of the sawtooth I would get. And I could get an even better approximation if I added in higher frequencies as well. So again, where you bow is going to affect the spectrum you produce. And why is that? The idea is that if you pull the string very close to its end, you're pulling it very near the place that it's fixed. It really wants to snap back. It's much easier to pull it in the middle. You have to pull hard to get it to move at the end, and it's really eager to snap back. So what happens is if you bow close to the end here, this snapping back is even faster. It comes back much more quickly if you bow at the end of the string than if you bow at the middle. And these sharp edges come from the high frequencies in the spectrum. So bowing up close to the bridge produces not just a louder sound, but also a sound with more high harmonics in it. That's an edgier sound, tends to carry better in concert halls. So you'll notice beginning violinists bowing way down towards the middle, and they kind of make this soft, mushy sound. You know, it's up Perlman playing the violin. He's always bowing up by the bridge. He's got that sparkling, bright sound that can light up a room with 1,000 people in it, okay? And that's because of the high harmonics in that spectrum. Okay. So the next thing we need to think about is not just creating the sound, but how the sound gets modified after the initial excitation of the string. And to think about this, I'm actually going to move away briefly from thinking about string instruments and talk about the voice. So the next question is, how does the sound that's created by the initially vibrating object, whether it be the string of a violin or the tube of a tuba, or, for example, the vocal cords of the voice, how does that sound get translated out into the world? So we're going to look at the vocal system of a person. And the way this works is that the initial vibrating system is your vocal cords down in your larynx. And for simplicity's sake, we're going to think of those as being essentially like little vibrating strings. You can adjust the pitch, the fundamental frequency at which these vibrate by adjusting the muscles in your throat to increase or decrease the tension in the system, just like a violinist tunes the strings on their instrument. So here are our vocal cords. They vibrate and they'll produce some sort of a spectrum. So here's the fundamental, the second harmonic, the third harmonic. As usual, all equally spaced multiples of that lowest fundamental frequency. But before that sound goes out into the world, it has to make its way up this tube, which is your throat and your mouth, and actually is also coupled to all the holes in your head, which I guess are your sinuses and things on the top. And tubes of air also have resonances. You know that because you've heard people play the trumpet and people play the French horn. All of those things are instruments. But even a very simple tube like this one plays notes because it has resonant frequencies. So let's see if I can get some notes out of this tube for you. Okay, so you can hear, just like the little flute I played earlier, that this has particular frequencies of sound it would like to produce. Actually, they're very much like a string. The resonances have to do with the length of the tube. and with the speed with which waves propagate in air, which is 343 meters per second. So we have a set of resonances of this tube, very much like the set of resonances of a string. And because your vocal system has a tube in it, there are really two different kinds of resonating things. The vocal cords, which vibrate, and then this tube of air, which has its own special frequencies at which it would like to shake. So what happens is your vocal cords shake and produce some spectrum. But then the next question is, what happens to that sound wave as it comes up through the tube? And the answer is that because the tube also has particular resonances, some of the waves created by your vocal cords will be amplified because they'll be shaking that tube of air at exactly its resonant frequency, and so they'll get that tube of air shaking with a very large amplitude. Others of the frequencies coming from the vocal cords will be at the wrong frequency for the tube of air. So the cords will be shaken like crazy, and they'll shake that tube of air, but they'll only get a small vibration from the tube of air, and so they won't be amplified very much. So the final spectrum of your voice, the actual sound that comes out of the front of your head, has to do not with just what your vocal cords are doing, but with some combination of what your vocal cords are doing and then how this tube of air would like to vibrate. And you can sort of think of this final spectrum here as basically just being whatever the cords produce multiplied by whatever the resonances of the vocal tract are. These are sometimes called formants, these resonances of the vocal tract. This is interesting because we actually have control over the shape of our vocal tract. The vocal tract ends at your lips, and when you change the shape of your mouth, you actually change the resonances of that tube of air that's your vocal tract. And so you change the way that the sound that is initially created in your vocal cords is modified as it goes out into the world. And so that is, in fact, how you create different recognizable vowel sounds. So here's the spectrum of sound coming out from a person saying ah, like father. There's the wave that comes out. If they pick the exact same pitch, the exact same note, but instead say ee, like heed, they make a wave with a very different shape. And oo, again, makes yet a different wave. So the shapes of these waves are determined by the way that the vocal tract tube is shaped by altering your mouth. And so you're changing the shape of the wave, therefore you're changing the spectrum, and you're changing the spectrum by doing things to these formants, by doing things to the resonances of the tube that is your vocal tract. There's a couple of things that are interesting to note about this. These are the formants, these peaks here, the resonances of the vocal tract that just regular untrained speakers have. Opera singers and other people who sing a lot on the stage have an extra high resonance here around 3,000 hertz that goes way up like that they actually learn. And they learn to have that extra formant in order to be able to be heard over the orchestra. The orchestra is making lots of noise down here around 500 hertz. Okay? And if the singer all by themselves wants to be heard over the orchestra, they would like their voice, even if they're singing the same notes as the orchestra, to have lots of frequencies in it that the orchestra isn't producing, so that their sound will penetrate past the sound of the orchestra. And they do that by teaching themselves to reshape their vocal tract, change the formant, and create something up high here that ordinary speakers don't have. That's called the singer's formant. So that's how our voice gets reshaped from the strings in our larynx out through our vocal tract. Something very similar happens on string instruments. So here's a violin, and we've already talked about how you can excite different sorts of vibrations in the strings. But again, the actual sound that you hear comes not from the strings themselves, but from the result of the strings shaking the bridge, which is here, the bridge shaking the wood of the instrument, and the wood of the instrument shaking the air that's trapped inside that box. Okay? Just like the voice, the violin has what we call formants. Those are resonances of the body of the violin and of the trapped air volume inside the violin that depend on what the violin is made of. So this is the place where a Stradivarius violin is different from the cheap violin that your child starts playing in elementary school. So here you're looking at the formants for two different violins, the cheap elementary school violin on the bottom and the 17th century incredibly expensive violin on the top. And there are three particular formants that are most important for the quality of violin sound. They're labeled here with W's and with an A. So the W's are two particular resonances of the body, the wood of the violin, the frequencies that it particularly likes to shake at, and the A is the resonance of the bucket of air that's stuck inside the volume of the violin itself. So we have two wood resonances and an air resonance. And you can see that they're really quite distinct between these two circumstances. So the expensive violin has a much bigger air resonance, much more pronounced. It also has its wood resonances in different places. This is frequency along the bottom. So the wood resonances are lower in frequency and they're broader. Okay, so they're going to amplify. This being broader means it will amplify a wider range of frequencies produced by the strings. That's going to give you a richer sound. Now don't let me fake you out here. This does not mean that we figured out how to reproduce those fabulous violins of the past. We know that they do this, but we don't know how to make wood do that differently. Okay, so we understand what they do acoustically, but we don't understand how to manipulate necessarily the materials to create those particular resonances. Okay, so another really important aspect of sound that allows us to distinguish identifying sort of characteristic music produced by different instruments has to do with the way the sound actually changes over time from the moment that you first strike the string or blow the horn until the sound finally dies away. Though sound often is not constant over that range of times, here what you're looking at is the sound produced by an organ pipe. And this is the sound produced at the very beginning when the organ pipe is just starting to blow. And this is after a long time. It's the very same pipe, just one pipe. And you can see that it's really different. Right here it's wiggling fast, here it's wiggling slow, here they seem to be simple oscillations, here you've got some more complicated shape. So that sound really evolves in time. And that characteristic attack or transient at the beginning of a sound wave is part of the way that we identify and understand the sound that a particular instrument creates. So if we want to think about what this organ pipe is doing, we can again break this down and think about what frequencies, what harmonics are represented here, and that's what we're trying to show on the right hand here. So these are labeling which harmonics are oscillating, and you can see that at first the third harmonic is very strong, so we're having lots of these rapid oscillations, but it dies away quickly and is replaced by something that's mostly the fundamental. That's these slower waves, the basic, slowest, fundamental sloshing of the instrument. If you looked at these transients for a bunch of different instruments, you'd see they have a lot in common. It's very often the case that the high frequencies die out quickly. High frequencies, let's say on a string, mean sharp bends that are going back and forth very fast. Strings don't like to do that, and they dissipate energy that way very quickly. If you're just moving it gently and slowly in the fundamental, that tends to last longer. So you'll often see these fast oscillations at the beginning and slower oscillations at the end. It's also true that we don't really think about these transients, and so sometimes if we emphasize what they are, they can be a little surprising. Here's the first 60 milliseconds of the sound produced by a violin, stretched out 100 times so you can hear what's actually happening in the violin attack. That's less nice. So all of that scratchiness is actually taking place in the first tiny instant of the violin sound, and you think of it as that sort of strong opening to a confident sound, but it's actually full of scratches and all different kinds of frequencies mixed in there before the string settles down to mostly oscillating in its fundamental frequency in the way that we think. I've also got here for you some piano sounds. This is a piano sound playing a lovely little cantata. I think it's Bach, but they've electronically taken each of the notes and inverted them so that within each note, whatever the transient was going to be is at the end instead of at the beginning. So each note has been turned around. So from that, you can tell now, by hearing it backwards, the piano notes have this funny characteristic that they're very loud when they start, and they fade out towards the end. You heard the inverse of that in that tape, which sounded totally un-piano-like, right? Sort of organy at the beginning of each note, and then with these funny pops at the end. Normal piano notes going forward are loud at the beginning and quieter towards the end. So I'm actually going to show you now what happens when I play the piano into our microphone. And you'll be able to see that characteristic loud dropping off quickly and then long extended sound. I'll do it again. So you can see that the sound started off very big and then very quickly decayed down, but then lasted a long time at that low level. Pianos are actually very carefully designed to do that, to be both loud and sustained in a way that's actually sort of surprising. So pianos are unusual in the length of their sustain, what's called the after sound, that long, low-level sound that lasts a long time after the initial attack. It turns out that if you just take one piano string and hit it with a hammer, you only get the initial attack. You get that strong, bright, loud first sound, which decays away quickly, and then it just disappears. You don't have the long extended sound afterwards. You only get the extended sound afterwards by having more than one string for each note. If you look inside a piano, you'll see that for each note, usually there are 3 strings sitting right next to one another. And it seems kind of crazy. Why would you bother to tune 3 strings to the same note instead of just having 1 string for each note? Those multiple strings are what allow this long sustained after sound. And here's the way that people think that works. If you just have 1 string and you thwack it, it shakes, and then the shaking strings shakes the bridge in the piano and gives all its energy very quickly to the bridge of the piano, to the body of the piano, and out to the room. So the sound is loud and it dies away very quickly because the shaking string rapidly gives its energy up to the piano and to the room. If you have multiple strings all tuned to the same note, that first shaking string can, instead of giving its energy to the bridge and then to the piano, can just give its energy to the other string. They're tuned to the same resonance, they want to shake at the same frequency. So if the first shaking string gives its energy to the other shaking string and that gives its energy to the other shaking string, they're passing energy back and forth between the strings instead of out into the world. That allows the sound to last much longer because it's moving around within the string system instead of going out through the bridge and into the room. So they've actually done experiments where if you have all 3 strings vibrating and you block the extra 2, Suddenly the sound gets much louder, and then it dies away very fast. And that's because if you block the extra 2 strings from vibrating, the 1 string vibrates more, but rapidly gives its energy out into the world. We hear a loud sound, and then nothing. So the sustain requires those 3 strings. It's a very carefully engineered transient. Okay, so we've talked a lot about the sounds that different instruments produce. And we've talked some about how we perceive those sounds. We know that our understanding of pitch has to do with the frequency of the sound. We know our understanding of tone quality has to do with the mixtures of different frequencies that are present in a sound. But it's only honest to talk a little bit about how our auditory system both receives and processes and finally understands sound. So let me tell you a little bit about how our auditory system works, and we can think about how it will influence our perception of sound. So what happens is you have a sound wave coming into your ear. Remember, that's a series of compressions and rarefactions of the air that are coming in at a particular frequency. And the first thing that happens is that sound wave comes in through your ear and is collected in your ear canal. Now, you'll probably realize right away that this ear canal is itself a resonant tube, just like this pink one. It will have particular frequencies at which it likes to shake, and that actually is noticeable. There are particular frequencies of sound for which your hearing is much more sensitive, for which you're able to perceive much smaller vibrations and actually notice them, and those are the frequencies which are the resonances of this canal. Now, once the sound wave comes in, it shakes your eardrum here, and then the eardrum shakes the series of little tiny bones, the hammer and the anvil and the stirrup, lovely old-fashioned names, and they in turn shake what is the core of your hearing system, the cochlea. So inside the cochlea, there's a long, flat membrane called the basilar membrane. And the basilar membrane is coated with nerve cells that connect to your brain. We knew we had to get to our brain eventually, right? So what happens is that that basilar membrane is shaken by the sound wave as it comes in. And the more the membrane shakes up and down, the more the hair cells get bent, the larger the nerve signal that goes to your brain, the louder the sound appears to be. But the basilar membrane does more than that. The basilar membrane is actually a finely tuned resonant instrument. So this green picture on the left shows you something about the basilar membrane. This is the end where the sound comes in, and this is the end that's all coiled up inside the cochlea. And you can see from this picture that the membrane is not uniform. The basilar membrane is thin and actually also mechanically very stiff at this end, and it's fat and also mechanically very floppy at the far end. And so different parts of the membrane are resonant with different frequencies of sound. What do I mean by that? If a high frequency sound comes in, it'll shake this stiff, short part of the membrane the most. So 20,000 hertz will shake this part of the membrane the most and will hardly shake the rest of it. That's the highest sound you can hear. The lowest sound you can hear, down at 20 hertz, won't shake this thin, stiff membrane at all, but it'll shake a whole lot down here. Now, the nerve cells are spread out all the way along the membrane, and they're mapped in your brain, so your brain knows, did this part of the membrane shake? Or did this part of the membrane shake, or some other part? So not only does the basilar membrane tell you how loud the sound was, which particular nerve cells are firing tells your brain what frequency the sound was, and therefore we assume also what pitch we would hear musically. So the basilar membrane essentially serves as a frequency map for sound. Now, we can think about this frequency map as largely responsible for our ability to discriminate different frequencies as different pitches of sound. But we can also think about it in terms of how sounds seem to us when they're played together or simultaneously. So this question of consonance and dissonance. What sounds sound smooth together? What sounds sound a little rough or grating? Okay? Now what I'm talking about here with consonance and dissonance is not what's pleasant or unpleasant or musical or unmusical, because those things tend to be culturally different among different peoples. But the question of whether something sounds rough or smooth is actually physiological. And here's why. So I've drawn for you here sort of schematics of what parts of the basilar membrane would be moving if you played two pure tones together separated by different intervals. If I just play one single pure tone, let's say just a pure sine wave, simple smooth wave at 200 hertz, I'll excite not just a single spot right here on the basilar membrane, but there'll be a little region that's moving up and down. Not just one little narrow stripe, but a small region that's shaking. The small shaking region is about a semitone worth of basilar membrane. In other words, this note and this note, they overlap a lot in terms of what part of the basilar membrane is shaking. They don't shake exactly the same part, or else you wouldn't be able to tell them apart, but a lot of the same parts of the membrane are shaking. So that means that if I play those two notes together, right, you're shaking the same region of the membrane, mostly, at two slightly different frequencies. So it's trying to go up and down at 200 hertz and also at 202 hertz, and it's jiggling around a little bit chaotically. Okay, we tend to perceive two tones very close together like that as a little bit rough, or sometimes we say dissonant. And we think that that has to do with the two tones exciting largely the same regions of the membrane at different frequencies. As you move the two tones apart from one another, often people start to say, now it sounds smoother. I can't tell you what I mean by smoother, but it seems less gritty a little bit. This interval, the minor third, is often the first one that people say doesn't quite sound so edgy or rough. And the minor third also corresponds to the situation when the two tones are pretty much separated in terms of what region of the basilar membrane they excite. If you go all the way out to a musical fifth, then the two regions of the membrane that are excited are completely separate. So because we find that having two frequencies exciting the same region of the membrane tends to give us the sensation of roughness, we can start to think about what happens when you actually play not pure smooth tones, but real musical complex tones in chords to your brain. Okay? So let's think about this. So in general, if you play an actual instrument at one note, you're getting not just the fundamental, but also some of many harmonics, right? F, 2F, 3F, 4F, 5F, all these different harmonics are vibrating. And so in fact, not just one region of your basilar membrane is shaking, but a whole bunch of regions, right? One for each of those resonant frequencies. Now what's true is that up at the high frequencies, the basilar membrane doesn't have as much room for each frequency to sort of spread out. So you can see here, like, the distance from 200 to 400 hertz is you know, pretty far down there. If you only had 200 hertz of distance here, they would be right on top of one another. So what happens is the high harmonics get squashed together all up at this last little end of the basilar membrane. And so even if you're just playing one note, if it has lots of high harmonics, those high harmonics tend to get squashed together up here and do some of this roughness-inducing overlap. Okay? So if you have a very pure tone, just the fundamental, it tends to sound very smooth. If you have a tone that has more and more of the high harmonics, it tends to sound edgier and ultimately rougher because the high harmonics overlap in the regions that they excite on the basilar membrane. So that's just one note. If I just have one note with all its harmonics, the more high harmonics I have, the more there are multiple frequencies exciting the same region of the basilar membrane, the rougher it sounds. So if I now add a second note, it's going to get really complicated, right? If I add a second note, I've got both fundamentals, both harmonics, both third harmonics, both fourth harmonics, both fifth harmonics, all spreading themselves across the basilar membrane. So in general, that's just going to be a mess. Lots of things are going to be shaking at lots of different frequencies. There'll be lots of regions of overlap and some roughness. But you can think about the situation where there are particular combinations of notes where if you put the fundamental and all of the harmonics down, adding the second note doesn't actually add very many new regions of excitation for the basilar membrane. Let's think about the simplest one of those, which is two notes that are one octave apart. So let's think about this C and this C, okay? How are they going to look in terms of the regions they excite on the basilar membrane? So I've just drawn that each region has a little skinny spike, but that's okay. So here's my low C, and really we know that that low C is made up of some fundamental and some twice that frequency, some 3 times, some 4 times, some 5 times for each of the harmonics. So these are all regions of the basilar membrane that'll be shaking up and down just from one note. Now I'm going to play the note that's exactly 1 octave above, exactly twice the frequency. What does that do? Here's the fundamental of the higher octave, here's its first harmonic, and the next harmonic, and what do we see? The fundamental of this one exactly lines up with the second harmonic of this one, right? And this harmonic of this guy exactly excites the same region as this harmonic of the lower note, and the same thing for the third one, and for the fourth one, and for the fifth one. So the octave is really exciting only places on the basilar membrane that were already excited by the lower note. No new regions are shaken. And this, we think, is part of the reason why the octave is thought of one of the most consonant intervals. Where you play those two notes, they almost blend into one. Sometimes it's hard to tell whether people are playing the same note in different octaves or whether they're playing in unison. That's because the basilar membrane is excited in almost the same way if you have just this note or this note plus the note that's exactly 1 octave above. So maybe that's why the octave is thought of as one of the more consonant or smoothest intervals that we can play musically. Now what about other sort of well-known musical intervals that people put in a lot of some kinds of Western music, for example? So here's the fifth, right? So this is like between C and G. That interval. That's another interval that people often say has less roughness to it. And we can think about that again in terms of the regions of the basilar membrane that are excited if we play first this note, and then the note that's a fifth above it. So here again is our bass note with each of its harmonics exciting the basilar membrane, and here's the note that's a fifth above it, 1.5 times the frequency. So here it is with each of its harmonics. Now it's not true that every one of the regions of the membrane excited by the second note was already excited, like was the case for the octave, but many of them are, right? So this one's new, there's a new region being excited, but this one overlaps one you already had. This one's new, and then the next one overlaps one you already had, and that continues to be true. So for the fifth, every other harmonic of the upper note already overlaps a place that was excited by the lower note. And you can go on and make the same argument for other musical intervals. The musical fourth has a ratio here of 4/3, so you get some overlap but a little less than the fifth, and continuing for many of the musical intervals. So it does seem like there's some physiological explanation for the particular intervals that people describe as smooth to their ears that has to do with the overlap of sounds on the basilar membrane. So to just give you an audio experience of that, I'm going to play for you here two tones that start in unison and then spread out to the octave. And perhaps you'll notice as you're listening that there are some moments in which the sound sounds rougher and other moments in which it sounds more smooth. noticed some moments when it actually seemed like things were almost buzzing, when there was a lot of roughness between the notes, and other moments when the tones seemed to come together and sort of converge in your auditory system. So this brings us to the conclusion of our 2 lectures on the physics of musical sound. I hope that I've given you a sense of how the sound is initially created in the instrument, how it's brought out into the world through the interactions of different parts of the instrument, and then how we process it within our auditory system, and ultimately, the final thing we haven't dared to talk about, how we understand that music within the context of our own experience.